Okay, welcome back to the session, topical lecture session. So my name is Takata. I'm a lead PI of the Thermal Physical Properties Division. I'd like to chair this session. We have 4 topical lectures in this session by 4 I²CNER PIs. The first lecture is given by Professor Tatsumi Ishihara. I will briefly introduce you. Okay. He graduated from Kyushu University and he got a PhD in 1986, and he became a research associate in Kyushu University. And then, so he moved to Oita University as an associate professor. Since 2003, he became a professor in Kyushu University. In I²CNER, he is serving as an associate director. So today's his topic is hydrogen production by using solar energy. Please go ahead.
Thank you very much, Professor Takata, for introducing me. My name is Tatsumi Ishihara. I'm an associate director of this I²CNER, but today I am the position of the lead principal investigator of the hydrogen production divisions. And I would like to introduce you on the activity of our groups. And our group is mainly focused on the hydrogen production by using the solar energies, the renewable energies. This is a holistic energy system approach developed or targeted in our I²CNERs. And as you can see here, the production of hydrogen of our teams is central of this scheme. This means the contribution of the teams is very strongly requested for the I²CNERs concept. And this I²CNERs is now the targeting to achieve to the carbon neutral energy systems. But in order to this, we use the hydrogen as the important energy carriers. Therefore, important is how to make the hydrogen efficiently and environmental compatible. And therefore, our issues to overcome in this group goal is the production of hydrogen without forming CO2 based on the photosynthesis type catalyst process or new efficient water electrolysis reactor combined with efficient solar cells. This is the principal investigator in my groups. And but roadblock at the moment is the hydrogen. Current hydrogen is not a clean energies, but we call the black hydrogen, because the hydrogen, during the production of hydrogen, there are a lot of the CO2 are formed. Therefore, from the black hydrogen to the green hydrogen, we need to develop some renewable. We need to develop some renewable energy process. Therefore, we started to use the solar energies, because the solar energy is only the infinite energies. And first of all, I would like to introduce you the photosynthesis. And we call our teams as artificial photosynthesis. But artificial photosynthesis now is very popular terms, and wherever in the world, every people say that our target is artificial photosynthesis. Therefore, there are many definitions. So the real photosynthesis is to the produce of the sugar from the solar light and also the carbon dioxide. And but unfortunately, the photosynthesis does not give the hydrogen. They only produce the proton. But the proton is not our interest. Our interest is to the energy carrier that is by the hydrogens. But if we focus on the photosynthesis in the meaning of the photosynthesis, when the Earth is burned, at that time there is no oxygen in the air. Therefore, the oxygen in the air is generated with the photosynthesis, and the CO2 is fixed in the Earth as the carbon by the photosynthesis. But what our activity is, to the human consumes oxygen in the air and then forms CO2 to get the electricity. Therefore, the opposite way of the photosynthesis is our activities. Therefore, the artificial photosynthesis is back to these directions, but unfortunately, we don't need to sugar so much. Therefore, our target is to produce hydrogen from the waters. Then we can use the hydrogen as the energies, and also the oxygen is back to keep to the amount of the oxygen in the air at the same levels. Therefore, the definition of the artificial photosynthesis is our group is to use the water to generate hydrogen and oxygens. And compared to the proton, which is mainly generated in the photosynthesis in the natural leaf, the production requirement energy for the production of hydrogen is much larger. Therefore, for the case of the efficiencies, in the real photosynthesis, the 30% theoretical max is the estimated, but actually for the cone, just 1%, and the grain is just 0.3% is the efficiency of the natural photosynthesis. And our targeted value is the around 10%, more than 10%. This is for the case of the photovoltaic cell combined with the solid electrolyte cells, solid oxide electrolysis cells. And in the case of the photocatalyst, more than 1% is targeted. And this value is come from the realistic photosynthesis of the natural leaves. And therefore, in my group, we cover to the two approaches. And one is the powder photocatalyst. This catalyst system is a simple system, but easily expanded the size of the hydrogen productions. But the low efficiencies and the separation of hydrogen and oxygen is requested. And in the case of the approach 2, we propose to the combination of solar cell with the efficient electrolyzers. And this process is more realistic, and therefore high efficiency and formation of hydrogen and oxygen separately is expected, but high cost and not easily expanded production size. Therefore, we need to have some more detailed study or the more engineering study is requested for the approach 2. And this is roadmap of our subject, and at the moment we are expecting that this approach 2 is more realistic. Therefore, after the material designs and feasibility studies, might we have some commercialization is expecting after the 10 years later. But in the case of the photocatalyst, we need to create a new science and then they expand to the engineering, and realistic science is coming from around the 30 years or the more than the later of the 30 years from now on. Okay, let me introduce further the detail of our activities. And the first one is approach one is the photocatalyst. The principal idea of the photocatalyst is come from the report by Honda Fujishima at 1972. At that time, they used the titanium oxide for the photoexcitations, and then they observed the formation of hydrogen and oxygen at much lower potential than the theoretical values. Therefore, even now, titanium oxide is widely used for the photocatalyst. However, because of only UV light is used for the excitations, efficiency of the conventional photocatalyst for hydrogen formation is quite small. And then recently, there are several number of the photocatalysts which can use visible light for excitations. However, the efficiency is still smaller by the single excitations. Because at the moment, the photocatalyst system, they use only the single excitations. And because of these single excitations, therefore, the excited electron is quite easy to combine to the hole. And then the excitation energy is released with the heat. Therefore, in our approach, we want to develop to the double excitation system, which is also used for the natural photosynthesis systems. Therefore, the achievement of the double excitation system, just like the photosynthesis for the water complex splitting into hydrogen and oxygen, is the main target of our groups. In order to do this, we used a very unique catalyst, like the inorganic semiconductor inside and covered with the organic dye outside. This is TEM image, and as you can see here, the inside is very highly crystalline KTaO3 perovskite, and outside is covered with chromium tetraphenyl porphyrin, and this is fiber layer is coated on the surface of this perovskite, and as you can see here, the structure is highly oriented, and therefore the self-organization of this organic dye is achieved on the surface of the inorganic catalyst. And according to our various experiments to characterization of this catalyst, we confirmed the first excitation occurred in this perovskite, and then the excited electron is injected to this organic dye, and then the second excitation occurred, and this electron is passed to the platinum. Platinum is coated on top of the surface of the organic dye, and then this platinum is works for the generation of the hydrogens, and hole in the perovskite is used for the formation of the oxygens. And this excitation system is really resemble with that of the photosynthesis in the plant. And this is the procedure of the photosynthesis in the plant leaf. And then as you can see here, they use the double excitation and they transfer to the excited energy to the second dye by using the proton. But this process is very slow. Therefore, in our system, the excited electron is directly injected to the dye. And this injection is quite difficult up to now, but we chose to the dye and the inorganic catalyst, then we can successfully achieve to the direct injection from the dye semiconductor to the organic dye. And then in this system, we are now realize that in these systems, why the leaf is used to this system, because of the charge was separated by the space. Because the two exciting system, therefore this hole and this electron is never the recombinations. Therefore, this double excitation system is quite useful for the separate of the charge by the space. And this is the current level for the hydrogen splitting in our systems. And as you can see here from the beginning, we observed hydrogen and oxygen, and of its formation rate is shown here is almost the double. Therefore, the formation of hydrogen and oxygen is achieved to the theoretical ratio to the waters. But unfortunately, on these systems, the energy conversion efficiency was much higher than the conventional photocatalyst, but still smaller than the 0.1%. This 0.1% is including the irradiations. But anyway, this conversion efficiency is much smaller than the solar cells. But we found very interesting the result. This is the transient absorption spectroscopy of the dye. And as you can see here, the once excited to the dye, then the separated charge never combined, never the recombinations. This means the positive charge, hole and electron is after excited, never the recombinations. Therefore, the excited charge is completely separated like the charged state of capacitors. And this state is quite effective for the highly efficient water splitting activities. But the reason why such the small conversion efficiency is come from the energy level of the inorganic materials. And this is the movie for showing the hydrogen and oxygen under the solar simulators. And this bubble is consists of the hydrogen and oxygen. And then as you can see here, we can see the such level of the hydrogen and oxygen. And at the moment, 1 liter of the hydrogen per hour is achieved by these areas. And then the reason why the conversion efficiency is small, although we achieve to the large separated state. And this is the UV light. This is the frequency of the sunlight, and this is conversion efficiency. This means if we use 100% of the UV to the electricity, the conversion efficiency is like at 5%. And if we convert to visible, then the conversion efficiency is around 55. And the current catalyst is used to the this level. Therefore, in the original, the energy of the ratio of the energy in the solar light is very small. That is why the conversion efficiency becomes very small. And then we started to find the new inorganic catalyst which used for the visible light for the excitations. And then this result is also the report introduced by Director Sophronis. But as you can see here, by using the zinc oxide doped gallium nitride, we can achieve to the use of the light level to the 500 nanometers. And then the conversion level is to the 2.7% apparent control efficiency at 402 nanometer light. And this was much improved to the previous KTaO3 systems. And then recently we applied to the another interesting result here. And in this experiment, we used the 320 nanometer bandpass filter for the irradiation. And then we measured to the second light, the formation of hydrogen as a function of the second light length, wavelengths. And as you can see here, if the excitation in the excitation in the gallium nitride doped with zinc oxide, then we can use the light up to the 600 nanometer, or sometimes much higher than the 600 nanometers. And this formation dependency of the formation rate on the wavelengths is quite similar with that of the absorption spectrum of the catalyst. And this suggests that the double excitation is very successfully achieved. And then if the inorganic dye excitation done at further higher wavelengths, then we can obtain hydrogen and oxygen by using the higher the absorption lengths. And also, I show here is the world top level of the absorption frequency of the each catalyst, and 600 is almost the highest reported in the open literatures. And the future plan is shown here. We are now the success to collaborated with the organic synthesis groups, and then we very successfully synthesis these kind of the new dyes. The color of this dye is shown here, and with increasing number of this ring, the color is changed to the more red shift, and then we can use the further longer wavelengths for the excitations. And up to now, we used this compound. This compound is very similar to the chlorophylls, which is used for the current photosynthesis. But by increasing the number of this ring, then we can use further longer light for the excitations. And data will be reported in the next annual symposium or some symposiums. And the next approach too is the combination of the solar light and efficient electrolyzers. This is rather the more engineering-like, because the solar cell has already commercialized, and even in these buildings we can use the solar cells. But the current solar cell consists of the silicon and consume a lot of energy for productions. Therefore, we focus on the organic solar cell, which is not requested the high energies for the productions. But in the case of the organic cells, the conversion efficiency is not so high. Therefore, we increase to the conversion efficiency of the solar cell to the organic type solar cell to the, for example, the 11%. And then we apply to the steam electrolyzers. And then if the steam electrolyzer conversion efficiency is around 90%, then the 10% of the conversion efficiency for the production of hydrogens. This is much higher than that of the photocatalyst. In addition, I also noted that this value, targeted value, is the same value with that of the DOE's solar hydrogen conversion efficiencies values. And, but in order to this increase in the efficiency in the electrolysis and the solar cell is requested, and this is our target. And the reason why we combined with the high temperature steam electrolyzer for this the solar hydrogen system is come from this thermodynamics. This is energy is requested the production of hydrogen as a function of the temperatures, and this is the energy obtained by the combustion of the hydrogens, and this is the electricity required for the production of the hydrogens, and this is heat. And as you can see here, with increasing of the temperature, the required the electricity becomes smaller because of the heat energy comes in. And then the increase of the temperature is principally desirable for decreasing of the electrical energy produced of the hydrogens. This means that if this heat can convert to the hydrogens. But the problem is that where we get this heat. And then our answer is that this heat might be used for the solar heat. This will explain in the later. And then today I would like to briefly introduce our approach on the steam electrolyzers. This is electric consumption for the production of hydrogen as a function of the thickness of the electrolyte. And this is the type of the conventional oxide ion conductors. And with increasing of the ionic conductivities, then as you can see here, the required electricity becomes smaller. And this LSGM is developed by groups. Therefore, by using this LSGM, we can decrease the required amount of the electricity for the production of hydrogens. And then this is the result, which is obtained in the previous by using the lanthanum garnet. And this is conventional cells. And in the conventional cells, we use the yttrium-stabilized zirconia for the electrolyte. And this is the case of the platinum used for the electrolyte. And we observe to the hydrogen and oxygen, which is very close to the theoretical Faraday's law. But compared to the conventional cells, although the operation temperature becomes 400 degrees Celsius lower, but by using, for example, this electrode, we can obtain more than 3 times larger amount of the hydrogen at the same 3 times larger hydrogen by the same cells. Therefore, by decreasing of the temperature, and we also observe to the much improved stability of the cells. And then this is reversible operations. And for example, the solid oxide electrolysis cells generated the hydrogens, and then the obtained hydrogen can convert to the electricity for the reversible operation of these electrolysis cells. And then as you can see here, compared to the simple nickel iron anode, by combination with the lanthanum strontium iron manganum, we observe the reasonable large current densities and also the reasonable power densities. The cell is reversibly operated. And then this is the conversion efficiencies. And as you can see here, with increasing of the current densities, the conversion efficiency is decreased. But at the open circuit, we observed almost theoretical conversion efficiencies. And please remind that in these definitions, we do not add any the heat. That is why the theoretical conversion efficiency is higher than the 100%. And then with increasing of the current, then the Joule heat is observed, Joule heat is generated, and then the efficiency is decreased and comes to the 100%. And at this point, we call the thermal neutral point, where there is no energy is requested to keep to the cell temperatures. But anyway, as you can see here, the thermal neutral point is come to 0.4 amperes per centimeter is observed on these cells. And then including the energies, the total energy conversion efficiency is close to the 0.95 for this current steam electrolyzers. And this result is also introduced by Director Sophronis. But Professor Adachi's group is now the study on the organic photovoltaic cells. And the current, they achieved to the 6.3% of the efficiency for the conversion efficiencies. And then in order to achieve to this, they control the interface. And here again, I show you the solar light, the spectrums. And as you can see here, by using this visible light, like a 600, we can convert to the electricity by using the organic solar cells. And for example, if our efficiencies, electrical efficiency of the organic cell increase to the 10%, then this part energy cannot convert to the electricities. And this part, light is infrared, or the middle wavelengths of the infrared is only changed to the heat. But this heat can achieve to the 500 degrees Celsius, which is not so difficult. And then if the conversion efficiency of this heat is around 3%, this means this 10% put it into the electricities, and the formed hydrogen is 0.25%, 0.25 is to use this heat. Then the total 3% of the heat can use among to these energies, and which is much smaller than that of the solar energies. And then the total, by combination of the steam electrolyzer and the photovoltaic solar cells, we can achieve the further higher, around 13%, is roughly, I can say, 30% of the energy conversion is achieved by these combinations. that is why this is a merit of the combination of the photovoltaic cells and the solid oxide electrolysis for the conversion of the solar energy to the hydrogens. Okay, let me conclude my talk. And the combination of the self-organizing porphyrin film with the gallium nitride doped with zinc oxide or the KTO3 achieves first-time double excitation and achieves the water-complete splitting into hydrogen and oxygen with G-type scheme. This G-type scheme is very similar with that of the photosynthesis in the leaf. And by exciting the gallium nitride doped with zinc oxide with the 320 nanometer light, then the visible light up to the 650 nanometer can use for the hydrogen productions. And in future, the application of the large ring porphyrin could further improve the formation rate of the hydrogen at longer wavelengths of the light. And the combination of the photovoltaic cell with steam electrolysis can achieve the efficient usage of the hydrogen energies and hydrogen with real clean energies. And although further improvement in the conversion efficiency and long-term stability are requested, steam electrolysis with efficiency higher than 90% is achieved by using the lanthanum garnet, which is new fast oxide ion conductor developed in my groups. So thank you very much for your kind attention. And these guys are from the Illinois collaborators, and then we are now make the good teams and develop to the solar hydrogen systems. So thank you very much for your kind attention.
Thank you very much, Tatsumi. So next speaker is Dr. Brian Somerday. He is a fellow scientist in Sandia National Laboratory. He joined that laboratory in 1997. And now he has joined a project seeking to develop safety standards, regulations, and standard formulations in the practical application of hydrogen energy, a form of energy being promoted by US DOE. So today's his talk is a mechanistic and modeling study of hydrogen-accelerated fatigue in low-strength steels. Please start.
Thank you, Professor Takata. And I wanted to just give you an idea of where I'm going to go with this presentation before I get started. I'm going to give just an overview, some background on the phenomenon that we study in this structural materials division. And I'm also going to give you just a high-level overview of some of the objectives that we have in this division. And then I'm going to be presenting essentially one technical story. And this technical story has multiple contributors. And the reason why I chose this particular story is not only am I one of the contributors, but I really felt like this story represents some of the pillars of I²CNER. And namely that I'm going to be presenting some basic research, some basic science, which is issue-driven. I'm going to show you that it's interdisciplinary. And I'm also going to show you that there's a very strong international collaboration. And these are three of the pillars of the WPI. And I think this is embodied in this particular project. I also just wanted to acknowledge that there's a number of our peers from around the world that are experts in this area of how hydrogen affects the mechanical behavior of structural materials. And it's a privilege for me to be speaking in front of them. I'm really glad that there's a presence of our community here today. I think that's due in part because Professor Murakami is organizing a symposium on Thursday, and so a number of the people are present for this event as well. So I'm glad to be speaking in front of you. So this is just some of the background I wanted to give on the phenomenon that we study in our structural materials division. And this is a slide that also demonstrates the technology driver for the research that we're doing in our division. So we are ultimately interested in what I just am going to call hydrogen-induced material degradation. And the reason why this is important from a technological perspective for storing and transporting and distributing hydrogen is that if we don't understand how hydrogen degrades the material properties, then this can lead to unexpected failure, which can compromise the safety and performance of a myriad of components in a potential hydrogen energy infrastructure. And just to give you two examples of manifestations of this hydrogen-induced material degradation, and one in particular, where it showed up in an application. The first I wanted to show you is a failure of a hose on a hydrogen dispenser at a fueling station. And so this flexible hose was being subjected to pressure cycles, hydrogen gas pressure cycles. And under the action of these cyclic stresses and the presence of the hydrogen, this hose experienced a failure, which led to hydrogen being released, which is a concern because hydrogen is a flammable gas. And so this was an example of what we call hydrogen embrittlement-induced fatigue failure. Other examples of hydrogen-induced material degradation are represented over here in components like bearings. And in each of these cases, there is some sort of stress which is acting on this component. The stress could be due to, let's say, the pressure stress from internal pressurization, or it could be due to rolling contact or sliding contact. But the action of the stresses in concert with the hydrogen material can lead to the degradation and ultimately component failure. This is an overview of our hydrogen structural materials division. There are essentially 3 sets of expertise that are represented in our division, each of which is important for achieving the ultimate goals of our division. There is a group of us that focus on fatigue and fracture, another group that focuses on friction and wear, and a third group which is focusing on materials processing. Now there's a lot of interaction among these groups, and there are a number of shared objectives among these groups, and the groups can all contribute to these. And just as an example of some of our division goals, we want to develop predictive models. This is one of the elusive goals of the community at large, and is certainly one of the goals that we want to address in our division because it's hard. And that's what we're supposed to be working on, are hard problems. And so we'd like to come up with predictive models that are based on the physics, of gas surface interactions, hydrogen migration, and the actual mechanism of material degradation. And another example of one of our goals is next generation materials that have improved resistance to this hydrogen-induced material degradation and at higher strengths. And so as I mentioned, the different areas of expertise are contributing to some of these goals, and some of these goals are also interacting. So for example, in order to make sure that we are developing the right next generation materials, we have to make sure that we're also developing advanced methods for measuring the properties of the materials. And so all of this collectively is leading to our ultimate goal, which is to optimize the cost, performance, and safety of hydrogen components. Now, just parenthetically, I wanted to mention that you see in our division, our director, and I wanted to mention to you that we had a competition among all the divisions to see which division would get the director, and we lost. So Petros said they were supposed to be having some fun with this afternoon, so here's some fun at Petros' expense. But seriously, Petros has been working in this area for decades. So he is one of the recognized world experts in this subject area. So I wanted to just give also some background on where I'm going to be going with this story. And one of the points I wanted to make with this view graph is that ultimately what we're interested in, or one of the phenomena that we're interested in, is the interaction of hydrogen with the material which leads to the degradation and can activate cracking. But there's a view that I think is underappreciated in the technical literature, and that is that it isn't just the hydrogen material interaction which leads to, let's say, how the material responds or how a component responds. And one of the realities with hydrogen is that it is not only an effective embrittling agent. There are other effective embrittling agents that are in materials, elements like sulfur and phosphorus. But what's unique about hydrogen is that it's very mobile at room temperature. And what that means is that we don't actually need hydrogen in the material before we load it to get this hydrogen embrittlement phenomenon. We can actually get hydrogen migrating into the material while we're loading it at room temperature. And that's why hydrogen can be such an insidious embrittling agent. And so what I'm showing you here with this schematic is the tip of a crack in a material. This is just a notional crack. You're looking at it from the side, and so this crack would be opening up. And so inside this crack, we have, let's say, hydrogen gas, which is represented by these dark circles. And so upstream of this embrittlement reaction, ahead of the crack in the material, there is a series of kinetic steps which is required to get hydrogen into the material. And these can involve steps like the gas phase transport, physisorption, dissociative chemisorption, and then the actual entry and diffusion. And so I think there's an underappreciated view in the literature, which has been emphasized by people like Professor Wei at Lehigh and Dr. Nelson at NASA, that we need to understand these transport processes as much as we understand the actual hydrogen material interactions if we want to understand the entire embrittlement process and try to predict the engineering performance of components. And that's basically what I'm saying down here, is that in our fundamental studies, we want to be focusing not only on the embrittlement reaction in the material, but also on these transport processes. And so this is a very wordy slide, but it's trying to introduce the particular story that I'm going to be talking about today, which, as Professor Takata mentioned, we're calling a mechanistic and modeling study of hydrogen-accelerated fatigue in low-strength steels. And so our objective, ultimate objective, is to develop a predictive model, a hydrogen embrittlement model, that's based on the physics of the gas surface interactions as well as the hydrogen-metal interaction leading to the degradation. So our approach is to make sure that we're conducting reliable experiments to map out the phenomena as a function of different variables. And then once we understand these phenomena and their dependence on the variables, then it makes it easier to formulate models and to exercise those models. But we want to develop and apply these models both to help to affirm the physics that we are invoking in these models, but also we want to ultimately make sure that they're predictive. And as I mentioned from the outset, one of the really gratifying parts of this activity is that it involves collaboration across I²CNER division boundaries and also research institution boundaries. And I'll introduce some of my colleagues right now, Professor Alex Stakoff, who is an assistant professor here in I²CNER, who's an expert in theoretical chemistry, Professor Rainer Kirchheim, who's also here today, an expert in kinetics and thermodynamics, in this case of gas transport and surface interactions, and our director. And our director has the ultimate burden in this project of trying to develop this predictive finite element model that includes not only the transport processes, but the hydrogen-metal interactions leading to the degradation. This has never been done before. And I know Petros is really excited about this opportunity as well. So I'm going to start off by showing you some experimental data. This is data that I've shown before. There's some additional data that I'm going to be showing in this talk as well. But just to give you some appreciation of what we're seeing with this data, is these are tests that were done in high-pressure hydrogen gas environments. These were done using these typical types of specimens that we would use in the laboratory. And so these are specimens that we use to apply cyclic loading. So we're interested in studying the effects of hydrogen on the fatigue crack growth. And we do this testing in devices that look like this. This is a pressure vessel that's in the load train of a mechanical test frame. And so we have to put these specimens inside these pressure vessels, fill the vessels with the hydrogen gas environment, and then we can apply the cyclic loading in concert with exposure to the hydrogen gas environment. We have one of these capabilities at Sandia. There are numerous of these capabilities here at Kyushu University, which really does make this one of the premier institutions for studying these types of effects. And what I'm showing you here with this data that we measure from these types of experiments is this is the crack growth rate, and so this is the amount that the crack advances per load cycle. And you can just think of this as the stress range, so the difference between the maximum and minimum stress we're applying to the material. And what I'm showing you here with the dashed line is that this is the rate of the crack growth in the absence of any environmental effect. So this is the rate that we would measure, let's say, in air. And then in these different hydrogen environments, and I'll explain the difference here, what we see is that as we increase the stress levels on the material, at some point we start to see the crack growth rates accelerate. And by accelerate, I mean that their growth rates are above those that we would measure in air, which is just due to mechanical driving forces. And what I'm showing you is that these experiments were done in high purity hydrogen, but also in hydrogen with small amounts of oxygen impurities. And this is important from a technological perspective because these environments may not be pure hydrogen. And what we find is that as the concentration of oxygen increases, we see that the stress level for activating these hydrogen accelerated crack growths is increasing. And these results seem to infer what I mentioned earlier, is that the transport processes are important. So the role of oxygen here is not oxygen isn't diffusing into the metal and somehow interfering with how hydrogen interacts with the metal. There's something about the way that oxygen interferes with the hydrogen transport processes. So all of these tests were done at a constant load cycle frequency. That is the frequency where we apply the cyclic loading. What I'm going to be showing you on the next slide are some tests that were done at a fixed stress level, but now we're going to vary the frequency of the loading. And what we find is that this is the same type of testing, the same type of apparatus, but now when we look at this crack growth rate versus the load cycle frequency, starting at this value of 10 hertz, which was representative on the previous slide, as we decrease the load cycle frequency, we see that eventually the crack growth rates come all the way down to the crack growth rates in air. And the frequency at which these rates decrease depends on the oxygen concentration. So for example, the circles are 10 parts per million hydrogen, and these crack growth rates come down to the rates in air at 10 parts per million hydrogen at a frequency between 0.1 hertz and 1 hertz. The reason why this is interesting scientifically, but the reason why this is also interesting technologically is that a lot of the hydrogen containment components that would be operating, let's say a pressure vessel at a fueling station, are going to be pressure cycled very slowly. And so if we do have some of these oxygen impurities in our hydrogen gas, we could account for the possibility that the oxygen is slowing down the crack growth rates, and we can do a more reliable life prediction. So we wanted to try to develop a model to explain all the behavior that I just showed you on the two previous slides. And to start off, we wanted to have some proposal, some hypothesis of what physics were operating. And that's what I'm showing here on this slide. And so our hypothesis, as I mentioned, is that this hydrogen accelerated crack growth is somehow controlled by oxygen modifying the hydrogen transport processes. And so our hypothesis is that oxygen absorption on the crack tip surface somehow inhibits the hydrogen uptake. And so I'm showing you the same schematic. This is our crack tip. And so oxygen is interfering with these transport processes, most likely with the dissociative chemical, with the dissociative chemisorption. And the extent of the oxygen absorption is going to depend on the amount of on the crack tip area. So the more area we have, perhaps the less effective this oxygen absorption would be. And this crack tip area is proportional to the mechanical crack growth rate, the crack growth rate that we might measure in air. And we're going to assume that the hydrogen uptake depends on the quantity of absorbed oxygen, that they're inversely proportional. So the more oxygen we would have on that surface, the less hydrogen uptake that we're going to have through these transport processes. And so based on these physics that I'm describing here, we want to develop a model that relates the adsorbed oxygen, and by inference, the hydrogen uptake, to the mechanical and environmental variables that we used in the experiments. So this was the model that we developed, and this is where Professor Kirkheim was instrumental. And I just wanted to also say here parenthetically that I showed these experimental results for the first time at last year's I²CNER annual symposium. And later that week, Petros and Reiner and I were sitting in an office in Inumori Hall. We were talking about these results. Reiner went back to his hotel room and started to scratch out this model. The point I'm trying to make is that this is really one of the benefits of an institute, is bringing everybody together in one place so we can have these types of interactions. And this is a really great illustration of that. So here's the basis of our model, is showing you, again, the profile of this crack. This crack is filled with a hydrogen gas matrix, essentially, and there's some oxygen, which is in that crack. And so oxygen is going to adsorb on the crack tip surface and potentially impede hydrogen uptake. And so we're going to assume that this oxygen adsorption is rate limited by diffusion, oxygen diffusion down the crack channel. This is really, I think, the foundation of the model. And so in order to describe this diffusion, we're going to assume a steady state oxygen profile down this crack. And so here's just an illustration of a potential oxygen profile down this crack channel. And we're also going to assume that the oxygen concentration or the oxygen partial pressure is 0 at the crack tip. And so this is our presumed oxygen profile. And when Reiner did all of the math, it's basically a diffusion calculation. And we assume that there's a mass balance between the oxygen diffusing down the crack channel and the oxygen absorbed on the crack tip surface. We come up with this formulation, where Z is the amount of the adsorbed oxygen. And you can see this model contains all of the experimental parameters from the data that I showed you. Parameters like the mechanical crack growth rate, the load cycle frequency, the stress range, and some others. And so what we want to do now is we want to exercise this model. But you can see that this model is also by inference it describes the amount of oxygen absorption by inference, it's also describing potentially the amount of hydrogen uptake at that crack tip. So this is an extremely busy slide. This was not my intention when I put it together. And so I'm actually only going to go through part of the results that are illustrated here, in part because it's really hard to see one of these plots. But for my convenience, I just pulled these plots directly out of a manuscript that Petros and Reiner and I are just in the process of finishing. And so it was convenient for me just to present them this way. But what I'm showing you here is we've exercised this model and compared it against our experimental results. And I'm comparing it against the experimental results, not only for the crack growth rate versus the stress range data, but also for the crack growth rate versus the load cycle frequency data. And for each of these cases, we can formulate the model so that if we assume that in order to get sufficient hydrogen uptake to enable the accelerated cracking, this happens for a critical adsorbed oxygen level on the crack tip. In other words, when that oxygen level is decreased low enough, we can get sufficient hydrogen uptake to activate the accelerated cracking. And this is how we can try to predict the mechanical crack growth rate that would lead to the accelerating cracking in these types of experiments. So these dashed dot lines are the predictions from this model, and we're comparing where these crack growth rates start to accelerate relative to our predictions. And what we find, without me going into all the details, is that the agreement is quite good. One thing that we had to do is we can't independently determine what this critical oxygen level is. And so we used one of these sets of data, essentially to back calculate this critical level of oxygen, and then using that critical level of oxygen, we're able to make predictions for the other data sets. So we're using the same critical level of oxygen over here to try to determine what is the critical frequency for activating these accelerated crack growth rates. And as I showed you before, for 10 part per million oxygen, this is the experimental data, the circles, we see the crack growth rate start to accelerate between a frequency of 0.1 and 1. And our model tells us that would happen at a frequency in that range. And so the predictive capability of the model seems to be quite good. And so this not only validates the physics that we've assumed in the model, but even this very simple model can give us some predictive capability that we could potentially even apply to engineering components. So once we finish the first draft of our manuscript, Reiner did some more thinking. And the model that I just showed you has a number of assumptions, and one of them that I didn't describe to you is that the oxygen diffusion is based on essentially a static oxygen concentration profile. And so notionally what we're doing for the model is that we're just opening up the crack, we're assuming a steady state oxygen profile develops, and then we're calculating the diffusion flux down the crack channel, and there's a mass balance with the oxygen that absorbs on the crack surface. We're not accounting for the potential of the crack opening and closing and how that might affect the oxygen distribution profile. So that's what Reiner did with the next version of this model. And essentially what he's showing here is that at the minimum tension position, so at the position where the crack is closed the most, we might have an oxygen distribution profile that looks like this. And the shading is just supposed to be representing the different oxygen concentrations. So this is the highest oxygen concentration, this is the lowest. But when the crack opens, we actually need to flow some gas into the crack to make sure that the pressure is equalizing inside the crack and outside the crack. And so what Reiner is showing here is that we might get gas flowing into the crack by laminar flow, and it originally has this type of profile, but then it quickly diffuses in the lateral direction. But what we'd ultimately wind up with is an oxygen distribution profile that looks like this. And so the oxygen distribution profile is actually fluctuating between these two types of distributions as the crack opens and closes. But when you work through the math, we essentially find a model formulation that's no different than the previous one, and the only difference is that we have to consider essentially a time-averaged crack opening. But this is very comforting that there's the same dependence on critical variables like the bulk oxygen concentration, the load cycle frequency, and the mechanical crack growth rate. So for now, we're sticking with the simple model. So complementary to a lot of this modeling that I just showed you, would say is a more macroscopic model. Professor Alex Stakoff, who is in the hydrogen production division, who's a theoretical chemist and an expert in density functional theory, wanted to do some modeling to help us get some better insights as to exactly what is oxygen doing to inhibit hydrogen uptake, but also why is it that part per million levels of oxygen can basically outcompete hydrogen for the surface absorption sites. And so what he did was a series of potential energy scans for hydrogen approaching an iron surface and oxygen approaching an iron surface. And I'm not going to go through all the details because I'm running out of time, but what Alex came up with was basically this schematic which depicts his findings, and that is at a certain distance away from the iron surface, both oxygen and hydrogen would just be moving in random directions. But as we start to approach that iron surface, the oxygen is going to sense the surface first. And so this oxygen is going to start to be drawn towards the iron surface at a distance that's further away compared to the hydrogen. And then in the next layer closest to the iron surface, both the oxygen and the hydrogen are sensing the surface, and so they're both going to be drawn towards the surface. But the force on the oxygen is stronger than the force on the hydrogen. And so this is just one possible way that we are getting some insight as to how part per million levels of oxygen can outcompete hydrogen for these absorption sites. And then there's as I mentioned, Petros has the ultimate burden in this activity. He is tasked with developing a predictive finite element model that includes the physics of the hydrogen transport processes as well as the physics of the hydrogen material interactions leading to material degradation. And what he's already started to work on, and no one has ever accomplished this before, is to try to include the transport processes. And so this is just a plot showing how the concentration of hydrogen ahead of the crack tip will vary as a function of the time constant that represents the hydrogen reaction kinetics on the surface. So I just wanted to emphasize again that this is a very collaborative activity involving collaboration within I²CNER and also across institution boundaries. And it's very interdisciplinary. It's a fusion of material science, theoretical chemistry, thermodynamics and kinetics, and solid mechanics. And then for one of the future activities for this collaboration is we wanted to try to conduct some of these fatigue crack growth experiments on some model iron-carbon alloys. And in particular, we wanted to look at the effect of grain size. And by looking at the effect of grain size, we might get some additional insights into the mechanism for how hydrogen degrades, how it leads to the embrittlement reaction. And so I've been working with Professor Takaki and Arnaud Macadre in our hydrogen structural materials division. And so this is another illustration of trying to work with people within our division who have different areas of expertise. And one of the advantages of I²CNER and being able to have access to these types of custom iron alloys is that there's probably no better place than the Japanese steel makers to get these types of custom iron alloys. And Professor Takaki has a lot of relationships in the Japanese steelmaking industry. And so these are just some micrographs of the materials that we've just procured. And so this is my summary. I'm not going to read through it because I've literally got 1 second left. There we go. I've got the yellow light. So as Professor Takata said, criticism is welcome.
Thank you very much, Ryan. The next speaker is Professor Naotoshi Nakashima. He received his PhD in 1981 at Kyushu University, and then he started work as an assistant professor in 1980 at the Kyushu University. Then he moved to, he was promoted to associate professor and then moved to the Nagasaki University. And he came back to Kyushu University in 2004 as a professor. Now he is a PI of fuel cell division. So his talk is nanocarbon-based novel fuel cell catalysis with very high performance. Please start.
Thank you very much. Professor Takata for the kind introduction. I'm Dr. Nakashima of Kyushu University, Department of Applied Chemistry, and also a PI of I²CNER. And today's topic is nanocarbon-based novel fuel cell catalyst with very high performance. So I'm very happy to talk about this title. And before going to my talk, I will tell you a little bit about our fuel cell division. This is a structure. Lead PI Professor Sasaki and Professor Tara, MIT, and Professor Gakura from ETH, and it's me. And we have many group members or collaboration members in our fuel cell team here, as I shown here. So I hope many of the people here in this to attend this meeting. So in the field division, we have many equipment or machine to test or examine the performance and the durability. And this is just some of them. And we have more in durability test laboratory, fuel cell factory, and here, and more. So this is an objective of fuel cell division. The goal should be understanding of a fundamental of solid-state electrochemistry to extend fuel cell science. But there are many roadblocks or problems that should be solved. So one of the main problems is durability. And I will focus on this topic today. And towards goal, we have many approaches using a new material, a new concept. So here is just a slide for SOFC. So as you know, SOFC operation temperature is very high, such as 700, 800. Then we need to lower critical operation temperature. And but for PFC, usually operation temperature is very low, just 80 or 70, 80 centigrade. And to improve the performance, we need to go up the operation temperature for PFC. So now, in our group, field cell division, we have many people who are very strong in SOFC, and we have people who are very strong in PFC. So that the collaboration of the people of SOFC field and the PFC field is very powerful, and this is one of the advantages of this field cell division. And yeah, once again, maybe I can skip. Yeah, PFC, a higher temperature to obtain better performance. And SOFC lowers the operation temperature. Okay, once again. So this is just a fuel cell roadmap. So PFC and SOFC. So final goal may be non-platinum catalyst, but not easy. But we are doing some effort toward this goal. And for SOFC, maybe operation temperature and durability is most important. So now let me go into my talk. Our topics, that is nanocarbon-based novel fuel cell catalyst with very high performance. So this is our group member. And this is carbon nanotube to this material. And then, first of all, why carbon nanotube? There's a reason. So we use single-wall carbon nanotube, multi-wall carbon nanotube, and both of them show remarkable properties compared to reference compound, steel or diamond. So as you see here, these carbon nanotubes showed very high mechanical strength, mechanical properties, and electrical properties. And density is very small compared to metal or diamond. So the carbon nanotube are one-dimensional and but very strong and light and flexible, just like a plastic polymer. That's the reason why many people have much interest in this new material, nanomaterial. And such a remarkable properties is due to the structure that is extended by conjugation structure like this I show here. So again, strong conductivity and small particle optical properties are very unique. And so I hope you believe that material is one of the promising future nanomaterial. But when we synthesize carbon nanotube, they are solid and insoluble in any solvent, so to use. So in many fields, a long time ago, we saw that it's important to extract them in a solution. So then we can use liquid carbon nanotube or ink carbon nanotube. That is much easier to use. And then how to solverize. I don't have much time to explain about this, but we have, for about 15 years, we have studied the project and developed many new carbon nanotube solverizer, including polycyclic aromatic compound like this, pyrene compound and porphyrin, and surfactant and polymers, and also DNA. DNA is a very good carbon nanotube solverizer. And so now we have many different kind of soluble carbon nanotube, and such material is very useful for very basic studies for nanocarbon, and also some bottom-up approach and top-down approach, including bio. And so today topics is fuel cell right here. We have published several papers in last couple of years. Then for future low carbon society, what are the next generation fuel cells? So our approach is to use a polymer electrolyte fuel cell, PEFC. Now for PEFC is social demand or demand from industry, the use of very small amount of platinum or platinum free, and operation temperature and humidity. So and durability may be most important. So this is just a type of fuel cell. One is PFC and alkaline type PFC, alkaline type fuel cell, and SOFC and PFC and MCFC. And in our project, we have two different PFCs, that is acidic type and alkaline type. And today, I mainly talk on this on the first topic, acid type PFC or proton conducting type. And when I have time, I will talk a little bit about our alkaline type and platinum free type fuel cell catalyst. So the slide shows the present fuel cell catalyst. So this is just a model, and at the center, as an electrolyte, people use naphthalene, and as a catalyst for anode and cathode, people use composite material from carbon black, platinum, and naphthalene. But in this conventional fuel cell catalyst, there are big problems, including temperature limitation and low reutilization efficiency of the platinum, and poor durability, also poisoning, CO poisoning. So to solve the problem, we replace carbon black to carbon nanotube. Because carbon nanotube carbon nanotube are electrically very durable, and their electron conductivity is very high, and their structure is very smooth, and such a structure may be useful for scaffold gas path. So that's the reason why we replace carbon black to carbon nanotube. And as an electrolyte membrane, we don't use naphthalene. Naphthalene is widely used material, electrolyte material, proton conducting material, but the cost is expensive, and their working temperature at usually 80 centigrade and 100% relative humidity. That may be not good. And our idea is to use polybenzimidazole, because when we use this polymer material, the working temperature are very wide, so we can use the material over 100 centigrade and non-humid. That is a great advantage for fuel cell material, because such a higher temperature is advantage for this problem. So this is a slide that how to synthesize PBI. So we have a synthetic lab, so we can synthesize PBI very lately like this. And this is just an image of the film prepared from this polymer. The thickness is different from 15, 18, and 18. So you can, when you see the picture, the structure is very film is very homogeneous. And so this is just the beginning. So the paper is published a long time ago. We use PBI to stabilize carbon nanotube, and the result like this. And when we measured photoluminescence, so you can see a spot here, right here. This is evidence, proof that the carbon nanotube dissolved by the aid of PBI. So dissolved carbon nanotube structure is individual. And then we can observe fluorescence from the solution. So here I show how we compare conventional carbon black catalyst and our method carbon nanotube-based material. For conventional method carbon black, onto the carbon black surface, platinum first deposit, and after that, naphthalene is added and mix it. This is a conventional fuel cell catalyst. And our method carbon nanotube are coated by PBI, dissolved by PBI first, and then platinum are loaded onto the surface of the polymer like this. And this is, so first, we measure multiple carbon nanotube PBI solution, and by filtration, we can make a solid like this. And by a TGA calculation, we evaluated the amount of polymer layer as 2.1 nanometer. That indicates that the polymer layer, so grain layer, there's a polymer. The polymer is very thin, just like monolayer of the polymer are coated onto the carbon nanotube surface. And then we have platinum were loaded onto the carbon nanotube composite, multiple carbon nanotube PBI by using a conventional method like this. And this is stem of the catalyst without PBI. So without PBI, the obtained platinum structure is very inhomogeneous like this. So here you can see many, but here you don't see any. But when you use carbon nanotube PBI composite, formed platinum structure is very homogeneous like this. And here diameter is just 4 nanometer, but we can control the size of the platinum. Yeah, this is just theme again, like this, enlargement of the same picture like this. So, yeah, this is just a model. Okay, after that, we measured electrochemical active surface area, or ECSA, by using cyclic Bohr thermogram technique, and SK value almost comparable to the conventional catalyst. So that is okay for us. Yeah. And after that, we measured MEA, membrane electrode assembly. So this is how to prepare MEA using our composites. So this is the cartoon model. By using this filtration technique, we can use a film. And procedure is very simple, and scalability is okay. And this is a cartoon model for our fuel cell catalyst for acidic. And here we use PBI or phosphoric acid doped PBI, and both sides, anodic and cathodic, we use same multiple carbon nanotube PBI or phosphoric acid platinum catalyst. This is our catalyst. This is our catalyst. And here PBI. So you understand that our fuel cell catalysts are composed of totally PBI, 100% PBI. We don't use naphthalene. We don't use carbon black. Okay, this is just a picture of our MEA membrane, and same is like this. This is a film and the catalyst both sides, and measure the performance, IV measurement, cell voltage, current density, and power density was calculated here. And so it's important to tell that our operation temperature is quite different from conventional. So temperature is 120 centigrade, and we don't use humid air. Instead, just air. So non-humid air is okay for our fuel cell catalyst. And perform in such a unique high temperature condition, our fuel cell reach this level of power density. This is quite high. And when we use film with low resistance like this, so we found that our fuel cell performance increased from here to here. Last time maybe 120 milliwatt per square centimeter, but when we decrease resistance, film cell performance reach almost double. And so this result indicate that we can improve the performance more. And 100 is rather high, but we can improve more in a year or 2 years. And I like to talk about durability of our fuel cell catalyst MEA. So that is the durability test was carried out stress testing based on the FCCJ protocol. FCCJ is the fuel cell commercialization of Japan. This is a paper. And so potential cycling between 1 volt and 1.0 volt cycling like this, and this is 2 cycle, and cycling, and then we measure IV curve, and then cycling, then measured, and to obtain the result of stress testing. And this is the result. So pink one is after 10,000. And even after 10,000 cycling, the performance is almost similar to the original level. And after additional potential cycling, 40,000, 90,000, and finally 400,000 here. So it's amazing, but even after 400,000 cycling, our fuel cell still alive like this. So this level is not very bad. Compared to this one, and the performance is decreased, but still alive. So that's a remarkable result. Yeah. So the conclusion of this part is that our fuel cell catalyst or MEA showed remarkable high durability for single test durability test. That means for 400,000 cycling, our fuel cell is tough, alive, and experiment was carried out non-humid and higher temperature, and performance is also very high. So that's our conclusion. So such conclusion, such high performance is derived from the superstructure design of a fuel cell catalyst, as well as carbon nanotube intrinsic properties. This intrinsic properties is very important. Okay, so I will move on to the next topics, alkaline type. So alkaline types have some advantage. So low corrosive, non-precious metal catalysts resulting in a significant cost reduction. There are, however, still problems to be solved for the practice use of alkaline fuel cell. One of the important key issues in the performance of the electrocatalyst includes the choice of the electrolyte together with the interfacial structure as active cell. And I show acid type our fuel cell catalyst. The cartoon model is like this. And when we dip this acid type catalyst in KOH, we can obtain alkaline type. This is very simple. And after that, we set up this kind of alkaline fuel cell by making after making MEA. And here for alkaline type, we use not PBA but anion exchange membrane from Tokoyama company. And here is both sides KOH doped fuel cell and measured performance by using the GDE MEA. Yeah, and the performance is shown here. So our alkaline type performance reach this level. Power density reach 250. That is very high in alkaline type. So we published the result about 1.5 years ago. But at the time, this is almost world top level fuel cell catalyst. And we now improve this result, performance. So now maybe I show a little bit about the metal-free fuel cell catalyst. So there are, okay, so yeah. Here is our composite, carbon nanotube PBI composite. And after coordination of cobalt ion, we heat it, pyrolysis or calcination at a given temperature. Then we can obtain carbon nanotube nitrogen doped graphite like this. And structure may be like this. And we found that this catalyst acts as ORR, oxidation reduction catalyst without the presence of platinum like this. But compared to platinum catalyst, performance at this moment are not very high. But in this case, we use multiple carbon nanotube. When we use a single carbon nanotube, performance improved like this. So, but anyhow, compared to conventional platinum type, we need to improve the performance. Anyhow, it's important that catalyst without using any platinum, that's platinum free. So this is our roadmap. As I show today, our fuel cell catalyst is remarkably durable. So we almost resolve this problem. And higher temperature operation is important, and we plan to do experiment at higher temperature, 150 over 200 centigrade, to get better performance and also durability. And we don't use naphthalene, and PBI is important in our fuel cell. And at this moment, we use platinum, but platinum alloy or carbon alloy is important for future project towards platinum-free. And this is just summarize future work towards real world for fuel cell. And this type, higher temperature and reduction platinum, maybe this level, and use of core shell structure may resolve this problem, reduction of platinum. And also alkaline type, other metal in place of platinum. We now use platinum. We need to use another metal such as low-cost metal. And platinum-free, acidic and alkaline, both acidic and alkaline need to find the best experimental condition, calcination temperature and molar ratio. And also, in place of carbon nanotube, we can use another nanocarbon material, including graphene and carbon black nanotube composite. So we have some results. So this is a present result. So you can see many platinum onto the surface of the carbon nanotube, but we can reduce the amount of platinum onto the surface of, so density pretty much difference. So now we just started to examine the performance of this catalyst. And core shell structure is important. Also, we can change metal from platinum to platinum, Ag and Au like this. And here is palladium platinum core shell. One of the PhD students just succeeded in the preparation of core shell metal like this. And here, core is shell is platinum and platinum core, and so this is overlay, and you can see a clear core cell structure. So that result indicates that we can reduce the amount of platinum. Yeah, I should stop. Okay. So this is our group. Thank you very much for your kind attention. Thank you very much.
Thank you very much. I'd like to invite the last speaker in this session. So Professor Kenneth Christensen from the University of Illinois. He received a PhD at 2001 in University of Illinois at Urbana-Champaign, and he became assistant professor at the Department of Mechanical Engineering, University of New Mexico in 2002. And currently, he is a professor and the Kritzer Faculty Scholar at the Department of Mechanical Science and Engineering, University of Illinois at Urbana-Champaign. And now he belongs to the CCS division as a PI. And his talk is carbon dioxide sequestration research for risk assessment and mitigation. Please start.
Thank you very much, Professor Takata. So my presentation will be segmented in two ways today. The first is I'd like to give you an overview of I²CNER's CCX activities, the breadth of those activities, and in particular the missions of those activities. And then I'll talk a little bit more focused about my own research efforts in this regard. So I think we all know the motivation, and that is a continued energy reliance on fossil fuels is of course leading to ever-growing carbon dioxide emissions, and even more green technologies still produce CO2. Here we see the growth of CO2 in time. And so this leads us to the notion that if CO2 emissions are to continue for the foreseeable future, we must do something to reduce those emissions, and capturing and storage of CO2 is one possibility. So the sequestration concept is actually rather simple. Geological storage of CO2 through injection in for example, saline aquifers. So we capture CO2, we inject it into the geologic formations. Okay. What we would like to do simultaneously is both maximize both injection rate and volume, but we'd also like to simultaneously minimize the notion of carbon dioxide leakage risks, okay? And in particular, safety is a first concern, a primary concern that we have. So in this regard, the main goal of what I'll talk about today and sort of the overarching goal of the scientific base of I²CNER's CCS activities is put toward predicting the fate of carbon dioxide in a number of different environments that I'll speak about today. So CCS possibilities in Japan. Wright has identified a number of candidate sites, both onshore as well as offshore geologic formations where CCS may be possible. Shown here on the right is a table that sums up all of these in millions of tons of storage capacity. And so the take home here is that both onshore and offshore sites have already been identified, and these sites can trap CO2 in a variety of ways, as I'll speak about. Okay, so before this is a practical solution to the notion of reducing carbon dioxide emissions, there are many considerations that we have to tackle. Okay? So widespread implementation of carbon dioxide sequestration requires, first, as I said, identifications of safe and stable locations for geological storage of CO2. The creation of methods for both safely and efficiently introducing carbon dioxide to these sequestration environments. The development of accurate prediction tools for long-term fate of carbon dioxide, given the details of the local environment. So this includes both geochemistry, seismicity, and a number of other variables that are critical to understanding the long-term fate of carbon dioxide. And advances in technology that can both monitor and perhaps even control sequestered CO2 over the long term. And finally, we really need to understand the impact should sequestered carbon dioxide somehow leak from a storage site, whether this is an onshore storage site or an offshore storage site where leakage could occur into the ocean. So all of these considerations really sit at the nexus of both fundamental scientific understanding as well as technology development. And this again, highlights something that Dr. Crabtree talked about earlier, in the sense that we have both fundamental science that leads to then development of technologies for eventual deployment of these systems. Okay, so in terms of scientific challenges, we really, to accomplish these goals, we have to develop scientific understanding, tools, and technology to enable design, analysis, and risk assessment of geological CO2 approaches. Okay? And so this really underpins the goals of I²CNER's CCS efforts, in that we want to collaboratively develop techniques and instrumentation to monitor carbon dioxide storage in both onshore and subseabed reservoirs. We want to understand the fundamental mechanisms of both short and long-term CO2 fate in high-pressure porous rock CO2 water environments. We want to explore CO2 dispersion and dissolution in the case of inadvertent release into the ocean, in the case of subseabed storage. And most importantly, and overarching all of this, is we want to advance our ability to accurately assess the risk of candidate storage sites and methodologies, as well as demonstrate viability through field experiments. Okay. So we really think the keys to success here are very close collaboration and cooperation between industry, government, and academia, and that's what underpins all of the CCS efforts in I²CNER. So this is the CO2 sequestration and storage division. The lead PI, Professor Yanagi, and a group of other faculty, both here at Kyushu as well as at the University of Illinois. There are three main focus areas of the division. There's the Monitoring and Risk Assessment Division, the Geological CCS Division, and then Ocean CO2 Interactions. So the number of goals here. There are field experiments and model development that are taking place between both the monitoring division, area as well as ocean CO2 interactions. We want to understand how to trap the CO2 in the geologic formations, and that crosses boundaries between the geological CCS division and those that are looking at perhaps inadvertent release into the ocean. And ultimately, what we'd like to culminate in is CO2 injection experiment in Japan. Okay, so let me give a sort of a broad overview of both the timeline of CCS as well as some of the scientific challenges that we face. So let's take year one. We'd like to inject supercritical CO2 into some sort of geologic formation. Okay? It's often buoyant relative to the pore fluid, which in this case is typically brine, and so it has a natural tendency to rise and want to migrate. So over time, we'd like to reach the point of mineralization. Okay, so we'd like to form carbonate. We'd like it to become part of the rock structure. This requires, unfortunately, local immobilization or trapping of the CO2 for these chemical reactions to complete. And that requires immobilization over, in this case, thousands of years. So there are intermediate trapping mechanisms. We have capillary trapping. Okay, this is on a 1-year time scale. We have hydrodynamic trapping, about a 1-year time scale as well. We have solution trapping, where the CO2 dissolves in the brine, okay? And that's about a 100-year time scale. And then our ultimate goal, of course, is mineral trapping. So we'd like to understand all of these mechanisms so that we can hopefully go from injection to mineralization and maximize the carbonate formation from the sequestered CO2. So here we have injection, and here we have the CO2 trap in the geosphere. The real challenge lies here, and this is a black box of sorts, where we have supercritical CO2 brine or water in the pore structure of the rock. Okay? And we need to understand the science of these interactions to be able to predict how mineralization will occur, and also to be able to predict the fate of the CO2 from a risk mitigation and assessment perspective. Okay? So we have both the scientific challenge of understanding physics of CO2 trapping. We also have the scientific challenge of understanding physical and chemical alteration of the rock structure. And we have a technological challenge, which really has to do with monitoring the fate of the CO2 over time. So just a few projects that are ongoing here in the CCS division. First, we have here a project on relation between survey-derived data and CO2 saturation for quantitative CCS monitoring. Right? So this is a dual-front effort. We have numerical simulations trying to predict the fate of supercritical CO2 in complex pore structures. Okay? Simultaneously, we have experiments ongoing that look at the relationship between CO2 and saturation and survey data. So, for example, measurements of elastic moduli. And then the linkage of all of this back to the numerical simulation. So the goal here is to do field monitoring, to develop simulation and predictive capabilities, and then merge them together into a predictive tool that we can use for assessing sites, for example, for geologic sequestration. Here's just an example of some of the monitoring efforts, and Professor Sofronis showed this slide earlier. And the idea here is to develop tools that can be deployed in ocean environments to both identify leakage into the ocean from subseabed storage sites, okay, but also provide critical field data from natural venting CO2 sites that presently exist in the ocean, again, to validate numerical simulations of these processes. Here's an interesting project where we're actually looking at something we term renewable CCS or bio-CCS, where we use coal for renewable energy. So the idea of bio-CCS is to convert injected CO2 to CH4, methane. Okay? So it provides a hydrocarbon resource in this case. So this is really tied, though, to the local microbiological environment. Okay? And so we're in the stage right now of evaluating the potential of bio-CCS, and this has to do with estimates of distribution of coal bed, in particular here around Japan, and then also developing methods to monitor these processes. Okay? So just to highlight the interactions that take place between I²CNER, the academics in I²CNER, industry and government of Japan in this case, we have a collaboration with METI and JCCS on the Tomakamai CCS project. Okay? This is a pilot scale sequestration project. It's collaboration with Wright on the Nagoka CCS project. Collaboration with JAMSTEC on a bio-CCS project. and also collaboration with Kyoto University on an Indonesia CCS project. So I²CNER is interacting with those in the region that have invested in the notion of CCS. So in the interest of time, let me shoot on to the research that we've been doing on trapping mechanisms. So what we have is a fundamental three-phase flow problem. We have a solid matrix, let's say the rock structure. We have a fluid saturating the pore spaces. Okay, so that would be the brine in our case, the salt water. And we have a fluid invading the porous medium, which is the CO2. Okay? And as I said before, we have these four trapping mechanisms. We'd like to hit mineral trapping, but we need to rely on the other trapping mechanisms to immobilize the CO2 locally. There's been a lot of work on theoretical models of two-phase gravity currents with respect to these sorts of two-fluid systems, but the available work is really primarily numerical, and so it really requires some experimental validation. And we'd like quantitative measurements within complex pore spaces to understand these mechanisms. So we're doing primarily experiments in initially two-dimensional porous microfluidic test beds, shown here. And here are some of the pore structure examples. We have effectively pillared structures. Okay, so here's cylinders, here other shapes. And what we'd like to do is infiltrate this with an initial liquid and then infiltrate ideally with carbon dioxide and understand how those two fluids interact. Okay? So here are the microchannel details. We have a set of porous structures in here defined by the height, diameter of the pore structure, and then we have the pore space in between where the fluid will migrate. So the experimental setup, what we'd like to be able to do is track both fluids simultaneously in time so we can understand the dynamics of the interaction processes between the porous space fluid, the brine in that case, and the CO2 that's infiltrating into the porous structure. Okay? And we do this with surrogate fluids. So we're doing this at low pressures, so we can't maintain supercritical CO2. So what we do is we replace our brine with a glycerin water solution and our supercritical CO2 with a silicone oil. Okay? We primarily do this to develop the diagnostics that we'll then deploy at high pressures using brine supercritical CO2. We track both fluids simultaneously by spectrally tagging the fluids with fluorescent particles. And then we separate those spectral signals into different imaging systems, and by doing that, we capture the dynamics simultaneously of the two fluids. Okay, so here's a movie where glycerin sits in the pore structure, and then we infiltrate with silicone oil. Okay? So the glycerin are the bright spots, the silicone oil in this case has been filtered out spectrally, and all you see are the pockets of glycerin that remain. So everything that's dark here is a silicone oil. So you can see here the front of silicone oil coming through. You see that it segments off patches of glycerin, and there are also patches of silicone oil that are segmented off. These are the capillary trapping mechanisms that I spoke about earlier. Okay, so capillary forces are causing some of this fluid to become trapped in certain regions of the pore structure, okay, and immobilized. So here's examples of fluid velocity fields, which is effectively a measure of the flow rate of the two phases through the pore structure. Okay? And so here's a zoomed in region of the porous structure. On the top you can see the glycerin phase, and on the bottom the silicone oil phase. Where there's glycerin, there is not silicone oil. Okay? And so you see that in this particular time snapshot, segmented regions of glycerin, and you see the front of silicone oil passing into the pore structure. And we can measure then quantitatively the velocity or the flow rate through these pore pathways. So here's a sequence of vector fields that show this penetration in a quantitative sense. Okay? So the coloring again is effectively flow rate, with blue being low flow and red, yellow being high flow. Okay? And so this is silicone oil that is infiltrating an already saturated porous structure. And what you see over time is you get the development of these high momentum pathways, okay? Very selective high momentum pathways through the porous structure. And we can track these over time. And sometimes they change, and you get these regions that are segmented off. But over time, you see that the silicon oil tends to occupy pretty much the entire pore structure. So what this does is it's a very simple fluid system, but it validates the experimental methodology. Okay? So the next step where we'd like to go is, now that we have the experimental methodology set, we want to develop high-pressure micromodels similar to this, two-dimensional initially, that capture actual supercritical CO2 infiltration into brine-saturated model pore structures. And this is for validation of numerical models. And I didn't get to mention this before. It was the slide where my presentation froze. But we're actually hopefully beginning a collaboration soon with Pacific Northwest National Lab on these high-pressure micromodel experiments. They have expertise in designing these systems. Okay, the last part of my talk, I just wanted to highlight a new satellite center project that has to do with simulations of pore scale transport. And these are very complementary to the experiments that we're doing. Okay? This is Professor Al Veloki and Charlie Worth, both of civil engineering at Illinois. And the goal here is very similar, is to develop a Lattice-Boltzmann simulation tool that will predict CO2 migration and transport within these CO2 brine porous media systems. So here is an example model, micromodel, porous structure, where you have low permeability, high permeability on top, low permeability on the bottom. Here's the porous structure, again, very similar to what I showed you before. They've done experiments with actual supercritical CO2 migrating through this structure, and they've also done numerical simulations under the same conditions. And this shows at least qualitative comparisons. So on the top of the experiments for various capillary numbers, and these are the overall displacement patterns. So white regions are where CO2 is migrated. Okay? And you see quite good qualitative comparison between the experiments and the model. And the idea here is to do more quantitative comparison that allow fine-tuning of the model to actually predict quantitatively the characteristics of the experiments. Okay. So with that, let me summarize. The primary and unified focus of I²CNER CC activities is really directed toward addressing the fundamental science that underlying technologies of CCS. It includes developing techniques and instrumentation to monitor CO2 storage in both onshore and sub-seabed reservoirs, understanding fundamental mechanisms of both short and long-term CO2 fate in the geosphere, exploring the notion of CO2 dispersion and dissolution in the case of inadvertent release into the ocean, and also advancing our ability to accurately assess the risk of candidate storage sites and methodologies, as well as demonstrating viability. Okay? And really the key to success here is collaboration and cooperation between industry, government, and academia, and that includes both within Japan as well as across the Pacific with the United States. Thank you very much.
Thank you very much, Professor Christensen. And in the end of this annual symposium, I'd like to ask Professor Kasagi, a program officer of WPI program, to give us the general comment.
Well, thank you, Professor Takata. I will not speak long. Director Sophronius, distinguished professors, and ladies and gentlemen, as a program officer for I²CNER, I would like to give a few words before closing this symposium and this great day. It still continues to reception. Okay. Let me first congratulate all the I²CNER members on the completion and opening of this wonderful research environment, and also the very nice symposium today. It was in the fall of 2011 when I started to work as a program officer over this program. 3 months later, the unprecedented earthquake and tsunami attacked the East Japan, as you know well. And now we are facing very difficult issues, such as recovering and rebuilding of the devastated areas, cleaning the radioactive contamination, and also revising the future energy plan under the severe constraints of declining population of this country, increasing the sovereign debt, and a possible global climate change. If we look at the world energy trend, it is stated in the recent IEA energy outlook, and also being talked about by Professor Crabtree this afternoon. Fossil fuels will continue to be used as a primary energy resource for the next several decades at least. Nuclear power will also be a major electric power source in our society. And we'll also see the massive introduction of new renewable energies with better performance, reduced cost, and improved reliability. That is our hope, too. In contrast, we in Japan have current concerns, serious concerns, such as decreasing self-sufficiency of energy, trade deficit due to increasing imports of fossil fuels, of which price is soaring. We cannot see no definite pathway to achieve Japan's pledge of reduction of the GHG gas emission within 20, 30 years. Also, the purchase prices of the feed-in tariff, which has been introduced very recently in this country, are too expensive, so that they should be inevitably reviewed and revised in the near future. Therefore, we should keep in mind that in both short-term and long-term, our future definitely hinges on the science-based energy policy making and also technology innovation for sustainable energy. In that sense, it is evident that the role of I²CNER is ever more important. Fortunately, the I²CNER has excellent assets. As we have heard this afternoon, such as high level of research work on production, storage, and the utilization of renewable energy, unique clustering of top scientists, and excellent working environment in Kyushu as well as in Illinois. So I believe I²CNER should fully exploit these assets. Before all I²CNER members, there are new frontiers of sustainable energy which are to be explored and advanced with interdisciplinary knowledge, mix, and interactions, as Professor Sophronis always emphasizes. You need to identify and focus on most important technology goals among diverse science and technology options and implement a continuous PDCA cycle. I'm sure that you will move forward bravely to that goal to meet global energy challenges. Now with this new building and facilities, you have new wineskins for your new wine. I hope it will offer an excellent platform for those coming from the world for collaborative research work and even for fusion of various disciplines to achieve breakthroughs in science and technology for future energy systems. I'm sure that the public, the government, as well as the science community all strongly want to see your substantial contributions to solving energy issues not only for Japan, but also for the world. So once again, I would like to congratulate all of you on the completion of this new building and another new start of this WPI base. I do wish all members further evolution and success in the years ahead. Thank you very much.
Thank you very much, Professor Kasagi. So now, do you have any comment? No? Okay. So in closing, so I'd like to thank all of the speakers and all participants to attend this annual symposium. So now the afternoon session is closing, and then soon we will start the evening session. Thank you very much.